Backpropagation. This tool helps you understand the concept of backpropagation in neural networks. Backpropagation is a fundamental technique used in training neural networks that enables them to learn from data. It involves a two-step process: forward propagation and backward propagation. During forward propagation, inputs are fed through the network and the activations of each neuron are calculated using the specified activation function, such as the sigmoid function. The output of the network is compared to the desired output using a loss function. In the second step, which is backward propagation, the network adjusts its weights and biases by calculating the gradient of the loss function with respect to each weight and bias in the network. This gradient is then used to update the weights and biases using an optimization algorithm, typically gradient descent. By iteratively repeating this process on a training dataset, backpropagation allows the network to adjust its parameters and minimize the error. This tool will help you understand the concept of backpropagation. Let's explore it. In this tool, we use a simple and well-known example of OR gate with sigmoid function. Here are the training steps, such as feed forward, backpropagate, next 10 epochs, and reset. We'll talk more about these buttons later. Here we have the epoch number, which represents a complete iteration, forward and backward, over the entire training dataset. The input number, which changes after each forward and backward step, and the learning rate is 0.1, and that is used in the training algorithm. These are the inputs, x1 and x2. Here we show the weights, w1 and w2, and we have the bias, b. The computed weighted sum, or sigma, is shown here. This sum is passed through the sigmoid function, and the output, y, is produced and shown here. Here, t is the target or desired output. E is the mean square error. Using this error function, the backpropagation values here are calculated as partial e by partial y by partial sigma, and so on and so forth. Using the chaining rule, the partial e by partial w1, partial e by partial w2, and partial e by partial b are calculated. Finally, these values, along with the weights, biases, and learning rate of the previous epoch, are used to compute the new values of weights and biases, and are shown here. Now let's start the training cycles by pressing the feed forward button. Notice how the weights w1, w2, b, and the weighted sum sigma are updated. Also, the system outputs 0.378, which was calculated and updated here. Note that the error value at the end of the first forward pass is 0.196. Next, we press backpropagate, and the tool calculates and displays different values of partial differentiation and the new values of w1, w2, and b. Now, the goal of this forward and backward propagation is to reduce the error value, or E. So if we repeat a few cycles of forward and backward propagation, the value of E should be reduced from 0.196 to some lower value. Let's try it. So I'll press the feed forward and then backward, and I'll do that about 4 times. There we go. And as you can see, the E value has now decreased to 0.189. We can always reset the system by pressing this reset button and start over as many times as we want. So I'll go ahead and I'll press the reset button, and then I'll do the same thing again. Feed forward and backward 4 times. Notice how the epoch number and input number change. Now, if we want to make big jumps to see faster convergences of the error, we can use the next 10 epochs button. So I'm going to press it. And please note that the error value has dropped to 0.142. This covers how this tool can be used to understand forward and backwards propagation in neural networks. Please feel free to try this tool by iterating through epochs and analyzing the behavior of the neural network in terms of backpropagation.